Okay, that works. So good morning, everybody. This is a high-level introductory lecture. We should have started with this, but unfortunately I had a meeting, I had to chair a remote meeting, which I couldn't move because there were like 10 people involved. So we get things the other way around. Also, normally I like to listen to speakers before me to comment and to respond, but unfortunately I missed, only saw half of Taka-san's talk, but I'll do my best to just give you a brief status update, more as a general reflection. And you saw on the previous slide already many abbreviations. I just tried to give you the bigger picture and a bit of a personal view on it. So to understand the migration we face, we have to understand how cryptography is used. We look at the quantum threat and how to monitor this, and then post-quantum and the migration. So if you look at cryptography, until about 100 years ago, it was only mechanical systems and used by the proverbial kings, generals, and diplomats. We got a first boost about 100 years ago when wireless communication happened and business people started using it to trade stock, and we got also electromechanical machines like the famous Enigma machine. And then in the 60s and early 70s, there was electronics involved, and finance world started adopting this. And then Diffie and Hellman invented public key in 1975. But in fact, they couldn't implement it. So even Rivest, you can look up the history, Rivest in the 80s tried desperately to design an RSA chip, and he never succeeded. So in fact, the first RSA chips were only made in the late 80s. And for example, in Leuven, a chip was designed, but it was actually a module of 6 chips, which was in terms of security a nightmare because the secret keys were probably flowing between the chips. But it actually could, finally we could implement RSA, which was actually not possible in 1975. So it was actually not used because it was too expensive. But we did get, of course, DES and triple DES being used in the financial world, and also the telco world started offering encryption for communications. And then a very big change happened. Cryptography moved to software. So computers became more powerful, and also people started designing algorithms for software like MD4 and MD5 with their bad fate, but also AES is an example of a cipher that also works very well in software. So then we also saw GSM, wide adoption of encryption for the wireless part, EMV specs, so European MasterCard Visa, the credit card payments now do is public key based, and SSL TLS was defined. But in fact, it was not that widely used, although it was there. To give you an example, in 2010 or 2011, the late Peter Eckersley did a study of how many TLS servers there were. There were only 10 million servers, and only half of them had a working certificate chain. So in fact, there were only 5 million servers. Of course, the high-profile ones, the banks, the big tech, they had a working server, but it was, most servers were actually insecure. And it's only after the Snowden documents that people actually started panicking and saying, oh, we have to actually use encryption. And then we go, let's encrypt. And today we have more than 600 million TLS servers offering encryption. So we now have really large-scale adoption. And also in messaging, as an example, in the communication sector, we now use it much more. And of course, we also saw cryptocurrencies, another very big adoption of cryptography and even of zero-knowledge proofs and very cool stuff. And then, of course, now we're working on the PQC migration. That's the next big evolution. I didn't mention automotive here. I guess automotive, what we got was these things, car key fobs with initially terrible crypto. Today it has AES. There is even, we did a crack of the Tesla system. Tesla used a secure module with signatures to sign with digital signatures to actually allow to create new key fobs. It turns out that nobody checked the signatures. So they had a certified module, but nobody checked the signature, which of course didn't help. And then of course, car systems have begun driving computer networks. So there is authentication, sometimes weak, but there is authentication in there. We have legacy on CAN bus. It's a very big security problem there that you can't change the legacy. On the other hand, we have sophisticated entertainment systems that probably use a lot of fancy crypto there in the software libraries. And of course, we have now a lot of telematics or telemetrics monitoring and so on. I'm quite sure my car sends lots of information, in part over 3G, which is not end-to-end encrypted. And hopefully for some of the more sensitive stuff, they should use probably standard TLS or maybe VPNs. So in fact, the standard stuff has happened. And then Taka spoke to you about V2X. So I guess it's also a wide adopter, but not a big adopter. And there is still lots of legacy there as well. So I think there is about 90 billion, maybe 100 billion devices that use cryptography today, which is a big change because when I started in cryptography, there were probably only 100,000 or so. This is late 80s. They were very expensive, and in our lab, we didn't have any. You know, I could see them at Swift, or I could go visit in Switzerland. You could go to Omnisec or Crypto AG, then you could see crypto boxes. But back in our lab, we didn't even have them. We were studying them, but we didn't have them. Of course, we started to implement libraries in software in the 90s, also in our lab. And we also built, my generation before me, actually, Ingrid and Frank, they actually built DES and RSA chips. But there was not complete encryption boxes. So I will not go into the details, but about 60 billion of those use public key cryptography. And I can be off by 10 billion or so, but I think it's not so far away. It also depends whether you count cards and separate libraries and how many libraries on your phone you count. But it's everywhere. Also, maybe it's not to protect Alice and Bob. Most cryptography is to protect companies against Alice and against Bob. Be aware of this as well. A good example is your passport is not there to protect you. The cryptography is there to make sure that you don't spoof your nationality. Migration is slow. This is a very nice graph created based on the SSL Labs data. I think Gaetan Laurent made this graph. It shows you the migration of TLS versions. So the quick adoption, so what is the best version is the colored, the full colors. And the dotted lines is when they started disappearing. And what you see is that even TLS 1.3 after Snowden documents with verified libraries, with lots of adoption, lots of support, even then you see it takes actually quite a long time to get to 50 or 60%. So the time constant here is something like 10 years. It takes about 10 years to get everything updated. And by the way, this is the top 150K websites. That's the bad news. The good news is that probably there is now a bit more pressure and there is more movement. On the other hand, what we also see is protocol ossification, which means that people actually implement non-standard things in their middle boxes, or some libraries don't implement the full standard, and then if you upgrade the standard, in fact, they break. So that's one of the reasons. The other reason is that people just set something up and never look at it again, right? It's people who sell like systems in building automation or so. Maybe it has a remote monitoring stuff. They're not going to update the web server, which is in there, to a new version of TLS. Quantum threat, I guess, again, given that you come here, you probably heard about it, but maybe it's good to get the history and some perspective on what's happening. So there is Feynman, and some people also credit Manin, a Russian scientist, also David Deutsch. So there is at least the physicists in the early 80s started thinking about this, how we could predict physics processes and build computers that could actually solve the Schrödinger equations for them, so we would understand atoms and molecules and the subatomic particles better. That was their main motivation. And then there was this shock of Peter Shor showing that on such a computer, factoring in discrete log would be a fast Fourier transform. If you're an engineer, you know this is n log n. This is the core algorithm for many engineering applications, and it's very efficient. So finding a period is an FFT on a quantum computer, and more or less it Shor showed that you can factoring and discrete log can be reduced to finding a period. People built the first one, and the first claimed factorization was done in 2001. So 15 turns out to be 5 times 3. I'll come back to this. Then researchers started working on this already, I think, quite quickly after Peter Shor's paper. Researchers started, and so by 2006, there was already a community, and the first PQ crypto workshop was held in Leuven. By that moment, there were already 60, 70 people worried about this problem. There were several people who wrote their PhD thesis on this. So, for example, in Germany, Professor Buchmann was very active in stimulating this research. And of course, today we have large computers. We'll come back to that as well. So more or less, the simple version is exponential parallelism. You have entanglement and superposition, and these things make some things faster. And already, again, from the Snowden documents, we know that the NSA spent $85 million already in 2014. So this is 10 years ago. You don't want to know what they spent on it today, maybe more. So it's also not clear, but what you see in the press is really state of the art. I guess it's hard to figure out. Also, there is a study of McKinsey that says that China spent 14 billion, but then some say it's 4 billion. Europe has a 1 billion quantum program, the quantum flagship. But it's clear that Europe is dwarfed by what big tech is now spending. We don't have numbers, So the motivation is not factoring. I don't think that Google or Meta or Intel are into factoring. Of course, they will have a good customer in some governments, but that's not the main application they envisage. It's more chemistry, material science, and maybe AI. And there was a breakthrough, well, at least we'll come back to breakthroughs. There was a breakthrough. There's an estimate by Google that stood for a few years that said for RSA 2048, you need 4096 ideal qubits. There is some methods that reduce the ideal qubits, but then they require more computation, so the trade-offs are not completely clear. But this is a good number, about 2 times the number of bits in your modulus. And the estimate was 20 million physical qubits. So you have to have the error correction because the logical qubits have to be ideal. The physical qubits are noisy. And so the estimate was 20 million, and in the beginning of May, it was announced that this could be improved to about 240,000 qubits. So 2 orders of magnitude improvement in the algorithm side. There is also a result by Grover for symmetric key that says you should double your key lengths. And there is a very nice analysis by Sam Jacques, invited talk at Chess last year, and you can watch the video, and the main message is don't worry about Grover. There's no way you can implement this. It's not parallelizable. It's not going to be implemented in the next 30 or 40 years. It's not going to have effect. But of course, everybody likes to upgrade AES 128 to 286 because it's easy to do and you can just do it and it feels good. And there is nothing wrong with it, but in fact, it doesn't really help you too much. So again, just to show to the scientists, so some people believe that quantum computers can solve everything. It's just that the problems in P, BQP is larger than P, like factoring is in there. Of course, we still don't know whether factoring is in P, but I guess we hope it's not. But so it's not that you can suddenly solve everything, is what some journalists or what happens if some scientists make the press release and the journalists say this computer can solve everything. No, it's only for a very specific class of problems you can make progress. Already after Feynman's paper, so in the years following up, the 2 decades, there was quite some effort to increase the number of qubits and the number of gates. So this is a slide made by Leuven van der Sijpen. And so the interesting thing is that people explored many things, but they didn't get very far. Well, it was very cool physics experiments. So the first real factorization happened on a 7-qubit computer designed by IBM. So this is 2 PhD students in Stanford. The one is Leuven van der Sijpen, actually was a mechanical engineering student of KU Leuven, went for a PhD in Stanford, ended up in quantum computing, and is now a professor in Delft in quantum computing. And so after several years of work, they managed to establish that 15 is 5 times 3. So we moved along, and there is one big change. Quantum computers now get names. This is very different. This computer, was the sweat of many people, but they had no name. It was a very big mistake to not give them a name. Today, all computers get a name. What does it mean? Marketing gets involved. Why? Because if you spend hundreds of millions of dollars, then marketing gets involved, and they say you have to give your computer a cool name. So that's now what you see. Computers get cool names. Also, if you spend $50, $100 million per year, you have to have a breakthrough every year. If not, your budget will be cut. So there is actually a very nice website. I forgot to put it on here, but I'll put it on the final version of the slide. There's a website keeping track of all the projects. There is dozens of projects. There is new startups trying spin electronics, atom spin, electron spin, whatever. There is many, many wild ideas. Number of qubits is only one dimension. You also look at error rate, at the decoherence time. So in fact, it's like more 3 or 4 dimensional parameters. So the Microsoft qubits, people still don't even know whether they work, but if they would work, they would be much more powerful. So even the 8 bits of Microsoft, if they would work, they could be more powerful than the 1200 or 1100 of IBM. Based on what is public, it seems that Willow, the one of Google, is now the most powerful at this moment. At least can do a real computation, although it has less qubits. So, but the main message is don't believe the qubits hype, and there will be every month a new breakthrough. There has to be, because the money is being spent, so there has to be a breakthrough. Okay, so always read through the press releases. Also, those breakthroughs don't build up on each other. Sometimes they're in completely different technologies that afterwards actually get lost. But so, I don't think timelines have to be revised because of breakthroughs, because to actually make progress, we'll need breakthroughs as well. But don't overhype and don't panic. IBM makes very detailed roadmaps. and they change every year. If you ask the technical people about it, they say, oh, this is marketing. That's what they say. So it's interesting. Google has a much simpler roadmap. The Google roadmap says, we're now here, we have quantum error correction. This is important to see. So in 2023, Google announced one error-corrected quantum bit. And they're now working on make it long-lived. And then they say we have to make logical gates, scale up, and then a large computer. And Google doesn't put timelines, unlike IBM that says here is this, you saw the details with the number of qubits and so on. Google is much more distance, and yet they have the most powerful one. So they announced last month that they actually finally did the first verifiable computation. Because before what they did, they produced a random distribution, which is kind of, you can't really verify it. You can only say, I did this. On a quantum computer, which is several orders of magnitude faster than a classical computer. So the last time it could be still debated. Now I think experts seem to believe this is really now quantum supremacy. It's still not useful. So they're still not going to make a new molecule or do anything useful. But the first ones to get there. But now if you've been paying attention, so Google claimed or published for the first time one error-corrected qubit in 2023. So you may ask, how can it be that in 2001, 15 was factored? Because they actually had no stable qubit. How could they factor 15? And the short answer is they've cheated. They couldn't factor 15. And so there was a very funny paper appearing beginning of this year on replication of quantum factorization records with an 8-bit home computer, an abacus, and a dog. So more or less, what they do is they just guess, they make some guesses. And so these authors say we can just make our dog bark 2, 3, or 4 times, and that also guesses factors. And that works about as efficient as those computers. In fact, a friend of mine who is a theoretical physicist actually pointed me to some earlier work from 2013 in which some physicists already put a paper on arXiv pretending to factor large numbers on a quantum computer. And they submitted it to Nature, but Nature didn't like their title, and they had to make it now to oversimplify quantum factoring. So in physics, you're not allowed to insult your colleagues, like in cryptography, where you can break schemes. In physics, you have to kind of say this was an oversimplification. Not cheating, it's oversimplification. Very interesting how the cultures differ. By the way, some people claim to have factored RSA 2048 on a D-wave computer. It turns out that what they did was they chose P and Q differed by 2 or 6. And the computer could tell whether it was 2 or 6. Of course, you can also just guess the 2 and the 6 and then write the equation for P. Find with a square root, you can find P and Q. You don't even have to know it. There is a simple algorithm if P minus Q is small to factor. So again, that was a very big cheat. But again, if your university give you several millions to buy such a computer, you have to come up with a press release, right? Okay. So since we're in Germany, if you really want to understand what happened, you read the reports of BSI. Deutsche Gründlichkeit is still something. So they wrote a very long report looking at all technologies and looking at comparing the maturity. And I guess they'll be very busy with several scientists to update this every year because given the fast evolution, they look at all technologies. They look at all the stages of maturity. And so they said last year it took about, they expect it takes about 16 years. So they're kind of optimistic. Here was another very nice graph by Sam Jacques, the same person from Waterloo already mentioned. What you have here is number of qubits in the x-axis. In the y-axis, you have the error rate. And so more or less what we've achieved over the past 30 years is this gray zone here. That's what we've achieved. As you see, we reached a space where we can do error correction. Although, according to Google, in fact, there is only the Google result gets there, but I guess it's all a matter of interpretation, what you exactly achieved. But at least we've now reached that zone where we can do error correction, which means you now have corrected bits, but not for very long. So if you would want to do valuable stuff to make money, is quantum chemistry, you would have to be up here. And so there is quite some research trying to see whether with these computers we can already bridge this gap and maybe still do something useful. But it's clear also that these even if you get here, you will not be able to factor because that sits here. So this is the gap to be bridged. Okay? And this is the graph of 2024. So pay attention now. Look what happened to the RSA curves. So I mentioned this improvement. So the RSA curves have shifted to the left now by 2 orders of magnitude, which is on this scale about something like this, right? So the RSA curves have now come closer, but they're still far away. Okay. You can also ask the experts to make predictions. And Evolution Q does this on a regular basis. So more or less you ask experts how long do they think, what the probability will be, or is that they think that in the next 5, 10, 15, 20 years, a cryptographically relevant quantum computer will be built. And some people also looked at what these experts say, whether it's consistent over the years. And for 70% probability it's consistent, for 50% it's not consistent. So right, they predict the same number of years 5 years ago as they do now. So in general, I think it's nice. These experts know more about this stuff than I do, but these experts also get $1 million grants. So they're not going to tell you it takes 30 years because we'll be kind of against their own interest. So I think the main message is that experts disagree and it's very hard to predict what's going to happen. You have also Adi Shamir, who said in 2023 it will take at least 30 years. So he doesn't think he will see one anymore. I don't know how long he expects to live, but so he's kind of optimistic. From a cryptographic's point of view, he says it's not never going to work. There is also a very nice paper that appeared earlier this year, which is somewhat accessible if you're not a quantum physicist, that actually explains step by step what the gaps are that have to be solved. So that I can really recommend. It's a detailed paper explaining why it's not so easy and why we need several breakthroughs. In fact, it doesn't matter because more or less governments have decided that we can't take the risk anymore. That's more or less where we are. This is why we're here, because there will be a migration, whatever happens. So I think consultants like to talk about Q Day, this famous day. I really think this is marketing hype and scary. I think it's not needed at all. But okay, what we can use is Moscow's equation. This is important. So you say how many years will be until the first large quantum computer, or if you want to have the marketing term, how far do you think Q Day is ahead? Right? That sounds very good, but in fact, we don't know. That's the answer. And how long does it take to migrate? And I have a very nice data point here for you. One of the largest public key deployments is the EMV system. So if you pay by credit card, especially contact payments, this uses public key technology. There is a whole PKI run by Visa, MasterCard, and so on. And so there was conceived in the early 90s. I was somewhat involved. It was rolled out in the late 90s. And in 2012, they had decided they would do a migration from RSA to elliptic curve, and they were planning to complete by 2030, 18 years. Why? They have 4, 5, 6 billion cards, but you can make a card expire and you can replace your cards in 2 years. The problem is the terminals. I think at that time, 2012, they had 37 million terminals. Probably now they have a few 100 million. So upgrading the terminals is actually hard. And then after a while, they actually abandoned the project. They thought like, who cares? But now they restarted it. And now they think they will be done by 2035. So, and this is people who have money because, you know, they're the financial institutions, they print it more or less. So even they can charge us overheads, a percentage on all our payments. So even they take a very long time. On the other hand, we've seen, for example, Signal already has migrated, so that has not taken 20 years. So it's very much sector dependent. And then, of course, you have to take how long your data needs to be confidential. And for standard business, it's 10 years. And I guess then this is the only math in this talk. Then you should start migrating. I guess you've all seen this formula. 25 plus Q minus X minus Y. So if I pull in some numbers out of my head, say 15 years for, it means Q day in 2040. I take 5 years to migrate, so I'm quite fast, and I want 10 years confidentiality, then I should start migrating today. You should leave the talk and start migrating and not waste your time in workshops. You're already too late. I think an interesting thought is governments, the standard for classified data is 50 years. So if you plug in 50 years, they should start migrating in 1995, I believe, or even earlier, so even before Shor's algorithm. So now you understand why governments are so nervous and why governments are driving, because they're already in big panic that in 2040, the other side or the other sides in the multilateral world will start reading all the classified data. So this is, now you understand why governments are really pushing so much, okay? And this graph shows you the details. So we're now here more or less, we have standards, but then they have to be implemented, they have to be validated, they have to be deployed. And as you saw with Signal, it can be fast because there is one company, they have some researchers, they write a library, they roll it out to all the users and update. They can do it in a year or so, but if you have an HSM, that's a very different story. You have to have different chips, you have to change your software, you have to get it validated, you have to then get it rolled out to your suppliers, it has to be tested. So that's more like a horizon of 5 years. For signatures, you have a good news that in principle you can re-sign all your data the day before the Q day, and then you're still okay. But of course you will be too busy on that day, and also you don't know when it comes, so maybe you should also start migrating, but there is probably less urgency. Although we'll come back to this, and I guess for this audience, I gave this slide yesterday at the European Space Agency, where they still spend many of our good taxpayer money on QKD with satellites. So the physicists, they use QKD. I think it can indeed solve some problems for about 100 million systems, but we have 60 billion. And if you look at Europe, what is Europe doing? Europe is spending hundreds of millions on QKD and barely 10 million or 20 million on PQC as research money. So we got our interest completely wrong there. It's really only a niche thing, and even then it's questionable. So in post-quantum, we had the competition. I guess you're aware of this. It's a very long process because this was 2016, 2026, but we now know it will already be 2028, in fact. It takes a long time, but this was the first round. The main message is Lattice is the only thing that survives, except for hash-based signatures. And now we also have code-based encryption added to this. But I think the main lesson for non-cryptographers is you ask cryptographers, design me a public key system that's secure for 50 years or more. You get 82 designs, and about half are broken in the first 1 or 2 years. That's the main message of this. Don't trust us. We seem to be eternal optimists. Okay, so that's... So COSIC was very upset because we had an algorithm which was very nice called Sabre that lost out in the end against MLChem. So we were so upset that we broke several other finalists. So we broke COSIC, we broke Rainbow, multivariate based signature scheme, and now Bart is with IBM, but he now broke Nova, so Supernova. So if you don't pick the COSIC schemes like AES and SHA-3 done by Johan Damen from COSIC, then we will break your scheme. So this is the main lesson for NIST. So it started 2016. So in the meantime, actually ITF didn't wait, and they standardized XMSS and LMS. These are hash-based signatures. They're simple. Hash-based signatures have the weakest assumption. In fact, for most parts, only second parameter resistance. For some parts, need collision resistance, but still, it's a hash function. And they're very old. So the base schemes are from the 70s. On the other hand, XMSS and LMS are foot cannons. If you reuse your private key, then you will actually, if you lost your state, you will leak your private key. So the whole world thinks this is a nightmare. BSI thinks it's the best approach. We seem to have a strong disagreement there. So of course, the problem also is that BSI maybe only has a few HSMs to manage. But if you're a big tech and you have hundreds or thousands of HSMs all over the world, then you think maybe managing states of these things is going to go wrong at some stage. But BSI thinks it's not the problem. You just manage them, you follow the procedures, and everybody will. Although, also for Enigma, the procedures were not followed. So maybe even in Germany, the procedures are not always followed. So I think be very careful before you listen to BSI on this matter. I'm happy to discuss it with them. The competition resulted in MLChem, MLDSA, and SLH-DSA. So this is two lattice-based schemes and a hash-based signature, which is stateless. And then Germany and France seem to like Photochem, which is a lattice with less structure. And then the Germans still like Macalise. The French don't like it anymore. But more or less, this is where we are. Then NIST approved HQC-Chem. This is a coding-based scheme, which is in all respects, in terms of performance, worse than MLChem. So I don't think anybody will adopt it. It's more like you have it on the drawer just in case. And then there's also FNDSA, Falcon DSA, also very interesting. You'll see right away why we needed it. But to have efficient signing, you need floating point arithmetic. And there is nobody who knows to do it in constant time. The other problem is that Falcon DSA was submitted in 2017 or 18. It was selected in 2023 or 24. And at the moment it was selected, nobody knew how it exactly worked. which is not a good sign to me. If after 5 years you still don't know how it works, you really want to make it a standard. If you need an extra year to really figure out how to specify it. So, and the other thing is that these schemes had cool names, and then NIST made the very uncool names which are unpronounceable and unrememberable. Thank you, NIST. Okay, so if you want to find out, so Kyber is ML Chem, so ML stands for modular lattice. And so dilithium is a D for digital signature, so this is DSA, and then Sphinx, SLH is stateless hash, and FN, I guess, the abbreviation of Falcon. Why do we change these names? I don't know. There will be more signature schemes, as you will see. There is still a running competition, and then China is having its own competition, Japan is having its own competition, Korea has a running competition. So there will be lots of chaos, because there will be many more schemes, and they will all end up in ISO standards, I promise you. So people say, well, the schemes, they're actually slower. In fact, they're not slower. The only thing which is slower is nobody can beat RSA with exponent 3. Now, for encryption, you shouldn't actually use this, because the advice of experts is use 32-bit exponents. It's a widely ignored advice. In the best case, people use 2 to 16 plus 1. But of course, you can never beat RSA with exponent 3. It's just not possible. It's just so simple. It's squaring and then a multiply. You can't beat that, okay? But in fact, the post-quantum schemes, the lattice-based schemes, are faster than everything else. They're faster than ECC and RSA. Encryption, decryption, signing, verifying is faster than elliptic curve, faster than RSA signing or decryption. But keys and ciphertext are 3 to 15 times bigger, and public key and signatures is even worse. The sum is 15 to 30 times bigger. And this is the problem that Taka-san mentioned, that if you have small massive with a signature, it doesn't work anymore. Okay? And then also, we don't have like zero-knowledge proof, so we're still working on this, oblivious PRFs, verifiable PRFs, all these cool things that are actually now being used. We actually don't have post-quantum alternatives. Anonymous credentials, well, we don't have them, or they're not standardized yet, or we're still looking at them, so there is still lots of research to be done. This slide shows you the public key versus ciphertext. So you see here in the x-axis public key, y-axis ciphertext. So you see why ECC is unbeatable. Okay, 32 bytes public key, 64 bytes signature, or encryption is also very small. And public key 64 bytes, ciphertext 128 bytes. RSA is already a bit worse. And then the small lattice schemes are here. And then you have Macaleese, which is here, as a very interesting trade-off. So Macaleese is a huge public key, but very short ciphertext, shorter than RSA. So for some applications, if you can somehow fix the public key or move the public key over a slow channel, it's actually a very nice key. The French researchers have shown that the matrix of the code of the Macaleese code, what you do is take a copper code, make a random code, that this code can be distinguished from random into 272 steps. Panic. But I mean, first, the complexity of attack is huge. Second, we know it's not the random matrix, so you can tell it apart from random matrix, that's fine, but you can't find a structure. So of course, it's the first result since 1978, but still, I don't think it's a reason to try Macaleese. It's, I think, some unnecessary panic, and there may be use cases, but this is really nice. With signatures, this is from the signature zoo. Most of the information, I try to condense it a bit, so it's not as accurate. If you want the details, you go to the signature zoo. So security is post-quantum security, so ECC and RSA is not. Then the new schemes, I guess we hope they're secure, and then there are still schemes under discussion, so I guess the competition hasn't settled. I just took 2 performance data, public key plus signature size. Of course, you look at them separately as well, but I simplified it, and also signing plus verification time. Just to simplify, so otherwise it's too much data. So, but I think you can look at this graph in a very short time, and you see that you never get green. Okay? So in fact, here you have post-quantum insecurity. For the current standards, so more or less, LMS, well, maybe I should put this orange, because LMS is state-based signatures. There you get 1160, but again, dangerous to implement. MLDSA, 2,700 bytes for public key plus signature. And people try to reduce this, and there is only one scheme that does it, which is an isogeny-based scheme, keysign, but then the performance is about 200 times slower. And this comes down from 5,000. There has been quite some improvements, but it's still 200. Again, not acceptable for some applications, right? So the problem is not in the timings. In most cases, you're pretty good. In fact, you see RSA is pretty bad. RSA signing, right, is pretty bad. So in fact, in most cases, you do better than RSA signing. Of course, you can't beat elliptic curve signing, which is very fast. Verifying ECC is reasonably fast. But there is just no good trade-off, and even the new schemes are not really offering what you need. So this means that probably there will be more research. On the other hand, this is too late, because even these standards, so there is some speculation that maybe SkiSign or Hawk or Mayo will be standardized, but these standards will only be there in 2028, 2029. For many migrations, maybe too late already, because you can't wait for that. So more or less, I think I said most of the things here. Things I haven't said yet is that, of course, something you have to get used to is decryption failures. If you like Falcon floating point, noise sampling, so the side channel people are having a great time. But of course, if you have to implement this stuff, you have to start from scratch. 20 years of research on how to implement ECC and RSA in constant time and with protecting against side channel attacks, and fault attacks, you have to do it all over again. And we've seen the consequences. There is Kyber slice. So Kyber, this is MLCam, when it was still called MLCam. So Kyber slice is a timing attack on Kyber implementation, which was actually the one Cloudflare adopted. So it was not a random implementation. And you also have this problem called Focalypse. So if you want to decrypt, you also have to re-encrypt in decryption and check that re-encryption is correct. This is necessary to stop certain attacks. This means that you have to protect both encryption and decryption against side channel attacks and faults. So it's actually an extra overhead. Normally in public key, you don't care about the encryption. If the public key is correct, it's fine. But actually, here you have to make sure your encryption also doesn't leak information and is correct. So what we're going to do, most of us, mere mortals, is go to a hybrid approach. The NSA is going immediately to post-quantum, and the argument seems to be simplicity. They seem to have blind confidence in lattice-based schemes. Of course, we don't know what their reasons are, but this is, I asked somebody, and he said, I talked to an NSA guy, and that's the reason he gave. Of course, maybe the NSA gives you the wrong reason, who knows. So what we're doing is hybrid schemes. You could, of course, make it easy to migrate and encrypt the key once with ECC and once with MLCam, but then, of course, you're not long-term secure. And for signatures, it is easier. You can sign twice, and then you have to hope the verifier checks both signatures, okay? And so more or less, you have to have an AND if you really want long-term security. You have to check both signatures, or you have to first encrypt with one and then encrypt the result with the other. And as I said, it's 50 billion libraries. It will be fun for the next 10 years. So for MLCam, there seems to be no major problems. People can plug it in. Well, we will see some problems, but mostly it works. If you upgrade AES 128 to AES 56, that's fine, but then you should be logical, and you should also go to level 5, which nobody does, because all the performance data I show is for level 1. That's what AES 128 security. Now level 5, everything becomes again 2 times bigger and 2 times slower. And for HQC, it's even worse. So you have to be logical. And if you go for level 5, you will pay a higher price. And what I said so far about being faster may not completely hold anymore. And your keys become bigger and the problem becomes bigger. Then if you don't want to use level 5, well, then do use AES 56, I would say. It's kind of cheating yourself. For signatures, MLDSA seems to be the default option. But apparently making a standard is hard. So the question is, should you hash before you sign or not? Then you can't believe these things. So in MLDSA, what you do is you start from a seed, and from this you generate a matrix. So should you now store the seed? Is the private key the seed, or is the private key the matrix, or is it both? And IETF can't agree, because some vendors have done each of those things, and some people already have private keys where they don't know the seed anymore. So it was very interesting. I read in the blog post of Bas Westermaat and Cloudflare that IETF started with 26 variants for hybrid signatures. Okay. And then they managed to, after long meetings, cut it down to 18. And then they said, we're going to recommend 2 or 3 main schemes, but then after a lot of fighting, they only recommend like the focus on 6 of them. So this is really bad because IETF is not doing its job. NIST is not doing its job. And of course, there is vendors that have already rolled something out or implemented something and they don't want to move back anymore. So you already have post-quantum legacy fights. It's really amazing. I think this is bad for our community, and I don't know how to solve it, but it's not a good sign. So hybrid signatures, you thought like, oh, it's going to take a few months, or NIST will do this. No, it's a mess, and this is going to slow all of us down, and it means you'll have to pay attention to the details if you have to integrate products from different vendors. So signature applications, so code updates, that's one. I guess that the requirements are not so bad because nobody cares about the size of your signature. If a code to make a flashlight is 65 megabytes, who cares what the signature is? And also the speed verification has to be done at boot. Okay, you don't want to be too slow, but there was already so much happening at boot. I don't think the signature is going to make the big difference. TLS is doing very well. The problem there is that, again, Bas Westerman's blog on Cloudflare blog, Megaverno's post, explaining that every TLS exchange has 5 signatures and 3 public keys. And so the handshake signature, then there is the PKI has 2 certificates. The certificate is a public key and a signature. And then you have 2 signatures for certificate transparency to actually prove that the public key or certificate was registered in a database with at least 2 vendors. And so this shows you now that if you go to 2 or 3 kilobytes, as I showed you, suddenly sending the signatures in TLS 1.3, it takes something like 15 kilobytes. And this is a problem. Also, MLChem is already a problem because some MLChem also means that the client hello doesn't fit in 1 packet anymore. But it's worse, much worse for signatures because MLChem is still quite short and it's then 2 packets, but for signatures it's 15 kilobytes. So PKI will need a hybrid certificate, which means you have to first hybrid signatures and then hybrid certificate. And then also, if you send a certificate to a non-post-quantum client, they will crash. So you also have to give the old certificate. So it's going to be a nightmare. So I thought that hybrid signatures would be easy, but hybrid signatures are hard. And now hybrid PKI is even harder because you have to now sign the keys of the signature schemes. And if there's a gazillion ways to print hybrid signatures, and it's going to be a mess. And I already mentioned HSMs there. You have to wait for your hardware vendor and then your certification. So some things are easier than others. So it's going to be a huge software migration project. You have to do a risk-based analysis. You can't do it all. I mean, there was this for a long time. This consultant said, first make an inventory of all your cryptography. It's going to take you 5 years in some banks. Some banks have discovered that they have CAs they didn't know about, and so on. So it's a good way to clean up your legacy, but you probably have to first define what's important and start with it tomorrow. In parallel, start looking for all the other things you have. But if you wait until you're done with your inventory, you're not going to be able to meet the timelines. Then you also have to look at your dependencies and start charting at your suppliers. And it's going to be very challenging. So it's a 10-year agenda. So with messaging is easy because it already has been done. At TLS, there is quite some progress, although we'll see this is again a mixed story. Secure boot and upgrade if you want a hybrid signature. The nice thing at least is secure, like something like code update, the ones who sign and the ones who verify are the same party typically, right? The ones, you don't sign something that somebody else checks, so you probably produce the same software, or part of the secure boot software is the verification software. But still, it's more complex because it's a signature. So PKI will be hard. I mentioned this already, so ML-DSA will mean that you send 15 kilobytes. That seems to break some middle boxes and break some clients as well. So when we say TLS has been rolled out and is post-quantum secure, it means without the PKI. So it's not for signatures, it's only for encryption. And then the real nightmare is platforms. If you have a complex platform like the big tech has, and you have to upgrade this, and in part you depend on suppliers, good luck. And of course, what you really want, what everybody says, you should have crypto agility, you should learn the lesson, and next time you upgrade crypto, it should be easy. I don't think it's going to happen. And it's also a very difficult trade-off because you have tight timelines, tight budgets. And if you say, oh, we're going to make it easy to also replace the algorithms, your migration now will be much harder. So I think it's a very difficult choice. But of course, we all agree that in principle, if MLChem is broken, you should be able to replace it by MLHQC overnight, but it will not be possible for many cases. And I think the big question, which is not on my slide, and it's really interesting, I mean, there is so many consultants writing about PQC and so much Q-day bullshit, but how much will this cost? Do we even know? I think it's a huge number. It's not my competence to estimate this, but we know what it costs, and what it brings is we'll have the same as what we had before. So I can just tell you from a business perspective, it's not a good business. So there is quite some shouting happening in companies. The business divisions say, what is going to bring us? So this is why the regulator has to come in and say, you have to do it, otherwise it's not going to happen. So the good story is the browsers. So in March 24, Chrome on desktop, and in a very short time, everybody more or less migrated, and also messaging, single last month, had the sparse post-quantum redshift, again, with academic research, adding to this and a very quick deployment. So here's the link to the blog. I really recommend this blog. It's a very long blog post explaining a lot of things in this talk, but also what's happening in the internet world, at least from a Cloudflare perspective. It's, of course, a very Cloudflare biased perspective. It's a very interesting perspective. So I think it's good news, but it means that some people are working very hard to solve your problems. This is great, and they seem to be successful. But of course, as I said, they haven't solved everything. They haven't solved PKI, they haven't solved, which you'll have to solve as well. So it's only part of the solution. But so at least if you look at Cloudflare, which doesn't see the whole internet, but we're around 50% of the global internet. This is Netherlands, because my talk was in the Netherlands. The Netherlands is a bit worse. We find out Bulgaria is a bit better, but it very often depends also on how much people use mobile versus desktop. But to give you an idea of some other statistics, and this is not all from Cloudflare. The Cloudflare has 18 million TLS connections per second. Okay. And somebody else made a study and said that now 38% of top 100,000 websites is migrated. And then finally, this is data for the edge of Cloudflare. But if you look at Cloudflare, so Cloudflare is between the client and the data provider or the website provider. Cloudflare is in between. If you look at the origins, this is where Cloudflare gets their data, there only 3.7% has upgraded, which shows that, you know, the picture is not as rosy as you would think it is. So we should be very careful. If you get statistics, you get a good news show of 50%, but then if you look at the servers, it's actually 3.7%, the origins. And then this afternoon, we'll have a session on migration. So I will be very quick on this. More or less, I just want to show you briefly the things, and you can look at it more in detail. I think there will be a next slide showing everything on one slide this afternoon, which is easier to comprehend. I just think it's interesting to show the NSA. The NSA was very fast. You now understand why, because they're too late. And how much? Well, 30 to 40 years. So they're actually very nervous. So what is interesting for NSA is that they distinguish between the application. So they say you should already be started with software signing, and then networking, web browsers, operating systems, niches, and then custom. But their hard date is 2033. The other thing is that they only have level 5 and only Crystal Kyber and Crystal Lithium. So this is before NIST has molested the names. So they now will read out the document and say it's only MLChem and MLDSA. And then also, as I mentioned already, no hybrid, which nobody really understands, but because they're the only ones in the world who took this decision. So NIST has a timeline. It says more or less, if you have longer key lengths, you can go till 2035 and 2034. If you have shorter key lengths, you should be done in 2031. So actually, it's quite mild. It's like you still have 10 years, which the response of most people will be, okay, then I'll do something else now. But then the White House, one of the last executive orders of Biden was very interesting. I guess it was also in part a response to Salt Typhoon, the discovery that some large country in Asia has hacked all the telco infrastructure of the Americans, probably also of the Europeans, but we just don't make enough noise about it, or we haven't found out yet. But more or less, more security on our networking, BGP, DNS, and to decryption of voice. So don't use your phone anymore for government business. Deploy as soon as practical. and use TLS 103. This was the last things. It didn't take long, very much for Trump, 6 months to overrule it. So he kept most of the things. He got rid of as soon as possible, and he got rid of the international collaboration. So NIST should no longer work with all these other countries. We should just do things by themselves. And also, as soon as practical concept was being removed. But then there is some other measurements. So you have to now have a list of products that support PQC. So CISA has to make a list. I guess they're not working for now, so it's probably not happening because you don't get paid. And then you have to issue requirements for TLS 103. And also the requirement in call for tenders has been removed as well. So the US is actually putting a step on the brake. And surprisingly, Canada has always been very early because of the work in Waterloo and Michele Mosca and some others. So they actually have already version 4 of their guide. And they have quite strict timelines as well. You can look at this. The EU, this is really interesting. In 2024, the EU said maybe we should make a plan for a plan. And why is this? Well, it's because it's a long story. I'll try to make it very short. The member states have always tried to stop the EU from meddling with cryptography. So they rather have the Americans decide than the EU decides. And so BSI and ANSI and GCHQ and the Dutch Secret Service, they've always stopped the Commission from working on encryption. And they said, you don't have the competence. And Article 4 of the Treaty of Lisbon, says that this is national security and you should stay out. Of course, for something like this, it's a nightmare. Because if every member state has their own agenda and their own schedule and their own approach. So I think now the member states are kindly coming back from this. And so it's interesting that the member states, actually 18 member states said to the EU, can you please get ahead? It's very funny. So for 20 years, they've been stopping any effort of the EU to do something. And now they suddenly say, can you please go faster and do something? As an example, also ENISA did some lists for cryptographic algorithms. And then the member states say, you can't do this, you don't have the expertise. And we will not let you hire the expertise. But so they're kind of changing their position. I think also the situation geopolitically may have some impact there. We do now have a European body that decides on standards, which is in the context of the common criteria. So you may know that the common criteria date back from the 90s. And last year, there was a real breakthrough. Namely, the EU member states could agree that the common criteria were common among the EU members. It was really amazing to hear that the common criteria are now common. So it took about 30 years to decide this. It's of course still not widely used because it's expensive. And in the framework of this common criteria, which is called EU Cyber Certification Group, the ECCC, they actually added FrodoChem and MLChem. So you see the Germans and the French were active there. But then last April from this year, they said, and by the way, by the end of this year, you have to get rid of RSA 2048. Excuse me? Why? I mean, for signatures, what's the problem? Unless PSI has in their basement a computer to factor RSA 2048 in a few minutes, but I kind of suspect this is not the case. I don't know what's in their basement or in ANSI's basement, but I don't know. Very, very bizarre thing. And then, yeah, there is no transparent process. So more or less, this is the gods coming from the sky and saying, here it is, and shut up. So even in the US, where we criticize the US a lot, at least like what I showed here for the US was a draft. And everybody can send comments on this, even the Europeans. Well, until now, the Europeans could send comments. Maybe we can no longer, well, maybe they will now be ignored from now on. There will be an order, executive order to ignore European comments. But in Europe, we don't even have a discussion about this. It's just the government deciding this, and that's it. I think it's not very good. But then there is finally some solution came from the sky. So there is the NIST cooperation group. So Europe has created a tsunami of regulation, including the CSA, the NIS2 directive, the CRA, DORA, whatever, the DSA, the DMA. I could give a whole lecture about this, but more or less, Europe found one thing, NIST cooperation group, to actually wave a flag and say, we're going to force you to do something. So the member states have to make a plan by the end of next year. And more or less, the idea is high risk should be done by 2030, medium risk 2035, and low risk, well, whatever. And you'll hear more about this. This afternoon we'll discuss this also amongst each other. So government, as I said, they should have started in 1994. They're too late. And this is why they're pushing, and they're pushing their vendors. Healthcare has long-term confidentiality, but they have other worries so far. I don't think that they put this very high on their list. They have low budgets in general. If you work in the IT of a hospital, you'll find out that more money goes to medical equipment than to IT security and cyber security. Finance, they will be driven by regulators, so they will move because it's Singapore regulator, the Israel regulator, the ECB, the Bank of England, they all, I mean, the first two already have issued some stuff, and the others are kind of saying, start preparing because we'll come down on you. So the financial sector is now in full panic mode, and they're now shouting at all their suppliers. So there must be very interesting conversations because they say, please upgrade all your systems. And then how much will you pay? Oh, nothing. You have to do it for us. And why? Well, because the ECB tells us to. Well, it's very interesting. And then automotive, I'll have a slide for this, but in general, they have long product life cycles and software updates are critical. So I think this is also why they're actually moving by themselves. So this is time to wrap up. So automotive, we can discuss this more in the afternoon. I'll just give a brief overview. I guess software updates are very important because, of course, there is also a safety issue there. If somebody can change the update, or you can also let the engine run in higher RPMs. Or I guess automotive people know more about this. Very often, the same model of a car is physically the same, but there is only software separating the models. And you can upgrade things. And it has been called tuning, but now apparently this is also part of the design. So you don't want the signatures to be forged, and also not in 2040. Because if you design a car today, it will be still on the road, hopefully in 2045. And so this is definitely a concern. For communications, there is user data, so you would think that they're concerned about privacy. Although, so at least you don't want to broadcast too much. But of course, there is also quite some remote maintenance and monitoring of what's happening in the car. And I see that my car reports lots of stuff to an app that I have, but probably it also goes to many other actors. I'm still wondering whether my lease company gets it as well, and then the insurance company, what do they get, and then the brand, and then the team maintaining my car. I'm quite curious what actually is happening there, but I think there's lots of flows. And at least for some of them, it's privacy, for some others, it's integrity. I can imagine that also a lot of communication in the entertainment and so on just uses standard internet protocols, and there you can hope the rest will do the work for you. And the bottleneck will be there your PKI and HSMs. And of course, I already mentioned that not everything is done. Then V2X, you had a whole talk about, so I can be brief, but more or less the brief answer is that it's not brief. Post-quantum security signatures are not short. It was already a problem with ECC. It's going to be a fortiori a problem with everything that's short broadcast. And then the multimedia platforms, I guess they're in part run by big tech or in collaboration with big tech, so I guess you can count on the migration there. Because that's the only thing I forgot to mention, that in TLS, so indeed MLCAM is not a problem. There is the problem of the client hello, which no longer fits in a packet, and nothing says it should, but some implementations assume it does. There is also the problem that, in fact, many packets being sent are short packets. And for example, many apps set up dozens of TLS connections. It's bad design of the apps, but that's the reality. It turns out that if you blow up the key exchange and you don't do enough resumption and all the other tricks, in fact, all this post-quantum stuff kills you, or at least means a substantial overhead, although you would think in most cases, use a scenario, if you read a newspaper or so, you go to a review website, you download kilobytes or megabytes and you don't care. But in fact, it turns out that the way we use this stuff, we kind of assume the handshake is short. And if this assumption breaks, many systems will break, or at least will, in the worst case, break, in the better case, slow down substantially. And that may also affect automotive, by the way. Well, I guess the main message should be reduce your TLS connections. And I'm not saying don't use plain HTTP, but in fact, be more strategic in how you set up connections. And that's probably a long-term effort. Okay, time to wrap up. So I think we have to be very honest, and we don't know whether it will be a quantum computer. But of course, we all seem to agree we can't take the risk, or at least the governments have decided this, so now we have to move ahead. The buzzwords are risk-based approach, crypto agility, maybe, if we can, and then I would say EU-level strategy, what are we going to do? Because as a car manufacturer, you don't want to have different requirements for every country you bring out a car. I mean, it would be a real nightmare, I think. If this country says that you should update your update mechanism before that date, and that country says you should have your encryption mechanism updated before that date, and so on. If you got depressed, we'll probably get cool applications from computers, new materials, new stuff. So probably the world will be a better place if we haven't ruined it by then with AI and other stuff. At least what we can get from it is very positive. But I guess it may still take a while. I'm going to stop here. Thank you very much for your attention.